Hello, I'm Darrell Ford. In this video I want to demonstrate how we do lathe alignment. To begin with, we need an L-700 lacer. I'll explain all these things, but we need the L-700 lacer. We need a T261 target. We need an R358 interface. The way these things work, this is the 700 lacer. This is similar to some of the other lacers they have. This has a rear mount stud, half-inch stud on the back, and has an on and off switch on the bottom. We turn the lacer on and we get the light, a straight line lacer. There's a 9-volt battery here. I loosen these two screws, slide the cover off, and I can replace the 9-volt battery. It's not rechargeable. It's an alkaline 9-volt battery. There's a level on the top and a level on the bottom because we're going to be rotating this lacer from what we call the normal position, which is the battery on the bottom, to the inverted position, which is battery on the top. We put the levels there, so we may not go exactly 180 degrees, but with the level we're going back to the same spot each time, so we're going to get good repeatability as long as we have good bearings in what we have this mounted in. In the front of this, there's some openings. On the bottom, there's a little light, a little diode light. When I turn this on, the light comes on and it shows me that the lacer beam is on. There's a shutter here. I can close the shutter so the lacer beam does not come out the front. It's a federally mandated thing that we have. There's 4 small holes here, back in these holes, and they're labeled. The top one is labeled center line, and the ones that are on the bottom and outsides basically are angular adjustments. So what I can do with this is, using the angular adjustments, I can tilt the beam vertically, and I can tilt it horizontally to change the angle. The centering adjustments, I can make the beam move straight up and straight down or straight sideways without changing the angle. So for that, when I put this in a spindle, I can do a 0 and 180, and I can because I can change the angle so I'm parallel to an axis of rotation, and I can change the position so I'm on the axis of rotation. So the way we can do that is this T261 target. This is what we call a T261 target. This is a 4-axis target. In other words, it will measure its position vertically and horizontally, as well as its angle vertically and horizontally. It measures its position to 1/10,000th of an inch. It can measure its angle to 1/10,000th of an inch per foot, which is just under 2 arc seconds. This also has a level on the top and the bottom, so we can rotate this and always go to the same position. Now this, because it can measure angle and center at the same time, the way it can, on the top we have a photocell, and on the bottom we have a photocell, or a target cell, we call them sometimes. When this beam comes in, we have the target here, like this. We have a target cell here, and we have a target cell down here. When this beam comes in, it goes through a beam splitter. This beam splitter splits that beam 50-50. So half of it goes up and half of it goes down. The half that goes up hits a mirror here, it reflects over here, and it hits another mirror and comes up there and measures the position of the target. The other half goes down here, hits a mirror, it goes through, and it goes through a little telescope that we call, or a telescope that has a focal length of exactly 12 inches. So then it goes over here and it hits another mirror, it goes down, and this cell is measuring the angle. The way that telescope works, for one thing, this is our mounting stud. This is what we call a virtual target. In other words, we're not measuring here, we're measuring here. This is our because of the way it's designed and the way things are set up, when we take a positional measurement, the positional measurement is at the face of this stud here. So when we see the angle on this target, if we have a vertical angle of plus 5/1000ths of an inch per foot, it's telling me the rear of the target is high by 5/1000ths of an inch per foot. So with that, I can have the laser beam over here, and if this projects out this way at a normal position, when I turn it 180 degrees, it's going to project out this way, and I can see the angular change. And by adding the two together and dividing it by 2, I can get the actual angle of the axis of rotation and adjust the laser to be on that axis of rotation. The reason we would need to do that, we're going to put this in a 3-jaw chuck in the headstock and in the tailstock in this case. We could put it in a collet chuck, or we could just make up an adapter to hold it. But we can never get that laser beam to be perfect to the adapter, or the adapter perfect to the axis of rotation. So we have what we call mounting errors. And that's the reason we have the adjustments in the front of the laser beam, so we can eliminate those mounting errors. We can physically make those changes and eliminate those mounting errors. We're also going to have mounting errors with the target, but we can mathematically eliminate those. The target plugs into the R358 interface. This interface, all this does is takes the signal that is getting from the target, from the 2 target cells, converts it to a signal that the computer will understand. This has a battery in it. When the battery is fully charged, you can use it without plugging it in. If the battery gets low, it'll go dead, you'll have to plug it in. You can still use it with it plugged in. All right, let's get this stuff set up in the lathe. And I want to mention here, this isn't, I know it's not a real lathe, but I get pretty good repeatability out of this, basically what we call a headstock here. And I can move the tailstock, so we can get some, get you familiar with the software. And the lathe alignment is software oriented. It's relying on software. So you're going to have a hard time doing it manually. Okay, most lathes, any lathe I should say, you can put a 3-jaw chuck on the headstock. That's the best way to mount this, or you can use a collet chuck. So we would put this in the chuck. Get it opened up here. Just clamp it onto the mounting stud and tighten the 3-jaw chuck. Okay, so now I can rotate this whole headstock. That's what I want to do. I want to rotate that spindle. The object is to get the laser on the axis of rotation of the headstock. Okay, now the tailstock, sometimes they have a center in here. You're going to have to remove that center, and I just use a 3-jaw chuck in the tailstock as well. There may be ways of using some sort of adapter, but I just use a 3-jaw chuck. It works just fine. And we'll do the same thing. We're going to put the target into the 3-jaw chuck. Tighten the jaws. And with that, it's a tapered fit. This 3-jaw chuck is a tapered fit, so when I put this in there, it fits tight. If I slam it in there, I'm not going to be able to rotate it. But if I put it in there just right, I can rotate the whole chuck. That's what I want to do. So many people just want to rotate this target in the jaws. That we can't do that because the mounting error, we have a mounting error between this target and the center line of this tailstock. So we want to find that center line of this tailstock. So we need to rotate the whole thing. Okay, now this target has a cable on it, and this cable plugs into the R358. And we have 2 screws here to tighten up to hold it into the R358 so it doesn't unplug itself. All right, this is a serial device. So we have a standard serial cable here. The serial cable will plug into the rear of the interface. I call it the rear, some people call it the front. It's probably I call it the rear because that's why we plug the charger in. Back here there's a port for our charger. And there's also 2 lathes, so when it's charging, this lathe will come on. And when there's power to this, in other words, when I start the program and this is plugged into the computer, it's going to turn this on. It's not going to turn on by itself. The computer is going to turn it on and the computer is going to turn it off. So we have a standard serial cable. If your computer has a serial port, you just simply plug that into the serial port. If you don't have a serial port on your computer, most of your new computers don't, so we have a USB to serial adapter that will plug into the USB port. Our system will come with this USB serial adapter. It'll also come with a disk, so you have to load the drivers for this. If you don't load the drivers for the USB to serial adapter, it's not going to work. So yeah, that's very important that you have the drivers loaded before you start doing all this stuff. So this plugs into the USB port. That is the connections, the setup and the connections for doing the lathe alignment. All right, we have everything set up, so I'm going to start out and I'm going to turn on the laser. That's important. Always have the laser turned on when you start. And then we've started the program, and I'm going to make a new project here. So I'm just going to call this Lathe 1. So I can give it any name I want to give it, but it's just something so you know what you're looking at when you pull it up for review. We'll call it Lathe 1 and click OK. Okay, now if you look on the screen here, I've selected the 261 target. My database ID is number 2, and the target serial number in the R358 high resolution. Also, I have to tell this how many points I want to take. Now, what we're going to do, the object here, is I need this headstock to be parallel to this bed, but I also need to know how flat and straight this bed is. If this bed has a twist in it, in other words, it's not flat, or it's not straight, it's curved, something like that. I need to fix that before I can ever make this parallel to it. If this is curved or it is hilly, there's no way that I can make this straight line parallel to a curve. So it's important that we check the flatness and straightness of this. But also, once we've determined this is flat and straight, then we can determine the angle that this has relative to the bed. I can never align this tailstock to this headstock if this is not parallel to this. In other words, if this was running off at an angle one way or the other, as I move this forward, my position would change. I need this to be running parallel to this travel of this tailstock, so no matter where I move the tailstock, the alignment remains constant. So I have to tell this. Now I've taken a magic marker and I've measured this every 4 inches, and I know I'm going to have 1, 2, 3, 4, 5, 6, 7 positions. Okay, that's the easiest way to do it, is mark it out so you know what your increments are, where you're going to go to. Now if you're on a CNC machine, you can use your controller and tell it to move 4 inches or 6 inches, whatever increments you want to go in. So I said I have 7, 1, 2, 3, 4, 5, 6, 7 points. So that's what I'm going to tell it, 7 points. Starting at point number 0. The closest to the laser is going to be point 0. The farther I get away, that's the higher number. I'm going to move this in 4-inch increments. Okay, now the headstock and the tailstock dimensions. The headstock is bolted on here with a certain, you have bolts we need to know what the dimensions are of those bolts, because this will calculate shim for you. If this isn't parallel to the bed, it'll calculate shim for you and tell you how much shim I need in the front and the back, underneath, and on the sides to bring this headstock parallel to the bed. So in this case, I don't really have any bolt downs here, so we're just going to pretend. And I would measure the bolt pattern here, and I might say this, okay, I have a 6-inch bolt pattern from the A dimension here, from the front to the rear, that's 6 inches. Okay, so I would put in here 6 inches. And then it wants to know how far from the front bolt to the face where the lacer's at, or the front of the chuck. So we would call that 7 inches. The tailstock, same way. It's bolted down. It's usually bolted on here. So we would measure, and here I'd say this is 4 inches. And from here to here, or to the rear of the target, we'll call that 5 inches. Okay, here I was viewing the headstock, but I can also enter the dimensions for the tailstock here. If I want to view the tailstock, all I have to do is select that, and it basically just turns the picture around. Because when I'm standing here, the headstock's facing that way, the tailstock's facing this way. So, but it doesn't matter what I'm looking at, as long as I get the dimensions right here, the headstock and the tailstock dimensions. Okay, here we have the lacer position. Now when I'm standing here on this side of the lathe, the lacer's on my left. That's what we're seeing. Should I want to do the alignment from the other side, it's unusual, but some people may need to work from that side, maybe because the way things are bolted down. Then I can change my view. So I'm viewing it from the other side. It just makes things much easier when you can view it on the screen the way you're looking at it here. Okay, here we have some tolerance bands. So I want to know, I have to have a tolerance for the straightness of this. You have a vertical straightness and a horizontal straightness. Okay, so I'm going to say I can live with 2/1000ths of straightness on this. So I'm going to set this up for 2/1000ths. And a tailstock center. In other words, how far can I have this tailstock center off from the headstock? What am I allowed? I'm going to say 5/1000ths here. Now I know I'm opening up these tolerances quite wide, but I don't have the best lathe in the world here either. So my tailstock angular, in other words, what could I live with for this tailstock angle, angular-wise, vertically and horizontally? So, you know, I'm going to say 2/1000ths a foot. Tailstock saddle parallelism. Sometimes a lathe will have different ways for the saddle than it has for the tailstock. So what we want to know is what that parallelism is. What we would have to do is take a set of readings with the tailstock and a set of readings with the saddle, and then it would give us a parallelism of the two. In a simple lathe where the tailstock rides on the same ways as the saddle, we don't worry about it. The parallelism is what it is. So I'm just going to set that at 0. Okay, now I'm going to move on to step 2. Go down to the bottom of the screen to step 2 and click step 2. Now we're going to get numbers. Okay, these numbers, if you look on the left side, I have white numbers, vertical and horizontal white numbers. Those are my positions, and these are just raw numbers that have nothing to do with the alignment. Has nothing to do, it's just raw data. We have to capture data and do some adjustments. We have to make the beam parallel. This is just a starting point, okay? The yellow numbers are angles, the vertical angle and the horizontal angle. And because this is a plus number, plus 46 thousandths per foot, that's saying the rear of this tailstock or the rear of this lacer, one of them is off to the other one, 46 thousandths per foot. Okay, horizontally negative 5 thousandths per foot, so the rear is to the left. Now, that'll all be explained, you'll have graphics for that. But to begin with, we have to qualify this lacer. In other words, I explained we have these holes in the front, and we can use a 3/32 Allen wrench, and we can make physically put this beam on the axis of rotation. Because the target measures its position and its angle, what we can do is invert this, and if we look at the screen, it's showing it wants the lacer inverted. It wants the battery on the top. So we put the battery on the top, and we're going to record that by hitting the record button. Okay, it records that. Now it's showing that it wants the battery on the bottom, or it wants to be in the normal position. And when I put this into the inverted position or the normal position, I'm looking at the level and I'm making sure the bubble's in the circle. So I'm going to the same spot. Okay, I'm going to record this. And now what the computer does, it does some math. And it says, well, angular-wise, you're off this far from the axis of rotation. And that's going to show me here. And this is telling me how far off my centers are. Okay, so what I'm going to do, I'm going to take a 3/32 Allen wrench, and I'm going to adjust till these vertical angle and horizontal angles are 0. Always adjust the angles first. If I adjust the centers first, then I change the angle, the centers are going to change. I can't change the angles without changing the centers. I can change the centers without changing the angles. So which one do I start with? It doesn't matter. In my mind, I like to start with the larger number first, so I'm going to start with the vertical angle. Now, I have to, when I do the angles, I have to have the long end of the Allen wrench. The short end will not reach the set screws. I have to have the long end. So I'm going to push this into the vertical angle adjustment. And if I block the beam, you see I go off target. So I have to keep my fingers out of the beam, and I'm going to adjust this a little bit. I'm just going to keep adjusting. If I get my finger in the beam, the numbers are going to change. So I have to keep repositioning the Allen wrench. If the lacer turns, get it back to the Now I'm going to do the horizontal angle. So I'll put it in the horizontal one. Again, using the long end. Never start with the short end, always start with the long end. We're going to adjust so these are now, because of what I'm working with, I'm going to live with 1 or 2 thousandths a foot. Okay. Now you see what happened to my centers? They came in less than 1,000th. That's good. That's good. We don't need to worry about that. If I needed to make centering adjustments, I would use the short end of the Allen wrench and adjust those. But before I do that, I want to go back and I want to restart, clear the data. I want to do it again to make sure that this is set, and I want to make sure I'm going to have repeatability. If I can't get any repeatability, there's something wrong with the headstock. It's going to be a mechanical issue. So I'm going to clear the data, and I'm going to follow the instructions again. I'm going to invert the lacer, and I'm going to record that. Okay, now I'm going to put it back to normal. I'm going to record that. Okay, now I'm off about 7/10, so I'm going to tweak it just a little bit. When I was off that far to begin with, it's not uncommon to have to make a couple of adjustments. Okay, so now I'm going to clear it, and I'm going to check it again. Okay, I'm getting really good repeatability out of this. I could do this over and over. I'm going to have tenths, maybe 2 or 3 tenths, but for something like this, that's pretty good. If you're on a real good lathe with precision bearings, you get 1/10 repeatability easily. So, and we're talking 1/10 per foot. This is showing 1 or 2 tenths per foot of repeatability. So now we're going to move on. We're satisfied that we're on the axis of rotation, or very close to on the axis of rotation, close enough to live with for this machine. Now, one thing I haven't mentioned is the averaging here. This is a short lathe, so our numbers are not fluctuating hardly at all. Sometimes you'll be on a lathe that may be 10 foot long if you're on a large engine lathe, and because of atmospheric effects, the numbers can fluctuate a little bit. There could be some vibrations and you're getting a little bit of fluctuation. So what we do with averaging, in other words, when I click record, it's going to take 10 readings and it's going to add those together, divide it by 10, and give me an average of those 10 readings so we can reduce that number fluctuation. Okay, we'll move on to step number 3. Okay, now we have to capture data. Now here I have the tailstock back in the number 7 position. I can start here and take data toward the laser, or I can move it up here and start and move away. It doesn't matter. Because I'm here, this is where I'm going to start. So I'm going to go here, and I'm telling it here that I'm using the tailstock. I don't have a saddle on here. I'm not going to measure that. That's off. So we're going to measure the tailstock, and this is our direction. I'm going to start here and go back toward position number 1. So I'm going to click that. And now you see it jumps there. Now I don't have to do any rotations here. I'm just going to move this from position to position to position. So I'm going to record that. And I'm going to unlock the tailstock, put it in position, and then lock the tailstock. When you move the tailstock, you always want to lock it, because the way these things work, they're on a bed, and the lock locks that tailstock, always pushing it one way or the other and pulling it down. If I don't lock it, I'm not going to get repeatability. So record that, move it to the next position. Okay, go to position 1. Okay, I've captured that data. I'm going to save that data before I lose it. So I'll click Save, and data's been saved. And it's saving it because I named it Lathe 1. That's the way it's going to save it, Lathe 1. Okay, let's click on the results. When we go to the results screen, this will tell us whether we're in tolerance or out of tolerance for the flatness and straightness of the bed, or I should say the vertical straightness and the horizontal straightness. If we're in tolerance, that's good. Then we can go to the move screen if our headstock is out of tolerance. This will also tell us our horizontal parallelism is in tolerance. We have a green check mark there, but vertically our vertical parallelism is not. So if I was in tolerance on the flatness and straightness, or the vertical straightness and horizontal straightness, I could go to the move screen. So let's close this out, and I would click on move. Okay, now I go to the move screen. It shows me the angle of this headstock relative to the bed, and it's going to tell me where to put shim, how much shim, and these are live readings. So as I shim this up, you can see the picture changes. When I see in the results, if I go back to the results, if I look at this and I see, well, yeah, these are out of tolerance, but my vertical straightness and horizontal both are out of tolerance. So where is the problem? Is it all over, or is just one spot that's out that I maybe can fix? Then I can go to step 4, which is going to give me the plots. Now we can look in here and I can see, oh, if I fix this right here, I'd be a lot better off. So I may be able to make some adjustments here, or I may be able to scrape it a little bit and fix things. So whatever. So once I'm satisfied that everything is in tolerance, I have fixed the bed so that the bed is flat and straight, or vertical straightness is good, horizontal straightness is in tolerance. My headstock is parallel to the bed. Then I can align the tailstock to the headstock. I'm going to go on to step 5. Here, it's going to tell me it wants the lacer inverted. Now this is where we go a little bit farther into the Norman procedure. Now before, when we qualified the lacer, we did a little bit of the Norman procedure. In other words, I rotated the lacer 180 degrees, took a reading, rotated it back. The software calculated how far off the axis of rotation I was, parallel or angular wise and position wise. And I physically took an Allen wrench and I eliminated those errors right down to a few 10,000ths of an inch per foot, as well as a few 10,000ths of an inch on position. So I physically corrected the problem. But the target also has some error. So what we do with the software is we take a normal and an inverted reading with the lacer, and we take a normal and inverted reading with the target, and it calculates what those errors are and eliminates it, so we can see the actual misalignment. Now they're coordinated, so we give you graphics. First it wants the lacer inverted, so I'm going to invert the lacer. And I'm going to record that. Okay, now I'm going to put that back to normal, just like it's showing me. It wants the battery on the bottom, and the target, it wants the cable on the top. So again, I'm rotating the whole adapter, not just the target in the chuck. I'm rotating the whole chuck. So I want to find the center line of this tailstock. That's the object. We want to find out how much error there is in this mounting between that. So we're going to eliminate that. We're going to record that. Now if you look at the graph, it wants both of them, battery on the bottom and the cable on the bottom. So we rotate them back. And I can't stress enough, when you rotate these, make sure the bubble's in the circle. You're not going to get repeatability if you don't keep do that right. Okay, we'll record that. Now, these graphics here, we can see that we're out of tolerance on the angle and the position. And these graphics, these are live updated also, so if I was to change the angle here, we could see that. Or I can go on to step 6, which in step 6, this gives me, the other screen only showed me the angle, it showed me a little bit. This shows me that the target is high by 13 thousandths. It's also high in the back by 40 thousandths, almost 41 thousandths per foot. And again, these are live readings, so if I was to change this, you see the numbers, you see it changing. Okay, so you're going to have shim values here that tells you how much the front and back of the tailstock here. We're not correcting this, we've already corrected this. We're going to be moving the tailstock. This is going to show me how much to put underneath the front and the back to correct that, as well as side to side. We don't normally have shims for the horizontal movement. We just make straight moves, or we can watch the moves, or it's telling us how much. So if somebody was to put indicators here and watch their indicators, they know how much to move it in which direction. Then we could do the report, we could save the report and bring it up later and print it out later. So with that, that's pretty much how we align a lathe using the Lathe 9 program.